Welcome back, everyone. Last time we proved quite a few number theoretic results. So, let me recall the statements again. So, we proved Fermat's little theorem. First, we proved Euler's theorem that a to the power pi n is a to the power pi n minus 1 is divisible by n for any a coprime to n. Any integer a coprime to n, a to the power pi n minus 1 is divisible by n, or as it says that a to the power pi n is congruent to 1 more. And in particular, we took p, n to be equal to a prime number p, and then a is any integer which is not divisible by p, and a to the power p minus 1 is congruent to 1 mod p, or p divides a to the power p minus 1. And this was just simple application of the fact that z mod and z star, or the set of units in the ring z mod and z, forms a group, abelian group. So in particular, we saw we can multiply both sides of this by a, then we see that a to the power p is congruent to a mod p for any a not coprime to p. Or a to the power p minus a is divisible by p for any a which is not divisible by p. But even for a equal to 0, this is satisfied. So if I look at this equation in f p z mod p z, we get a to the power p is congruent to a mod p, or a to the power p equal to a in z mod p. So that's what it says, that x going to x to the power p is a ring homomorphism which is identity on fp. So x to the power p equal to x for all x belongs to fp. Okay, on z mod p z, x to the power p equal to x for all x in fp. So x going to x to the power p gives you an identity map on fp. But actually, so in particular, it's a ring homomorphism because it's an identity map. It's a ring homomorphism. It is injective and it is as well as it is surjective. So in fact, x going to x to the power p is a ring homomorphism. You can check independently. So that's what I said last time. You check by binomial theorem that x plus y to the power p, you expand it polynomial expression, and you look at all the coefficients by property of binomial coefficients, you know those are divisible by p. So you get x to the power p plus y to the power p equal to x plus y to the power p modulo p. Okay. For modulo p, x plus y to the power p is always x to the power p plus y to the power p. So that means x going to x to the power p is a ring homomorphism. You can check directly. That's what I said. This map is called the Frobenius map. This map has a name, x going to x to the power p is called the Frobenius. We'll use this map later, so I'm introducing it. Now, another thing we saw of this application is the Wilson theorem. So you consider the polynomial gx equal to x to the power p minus 1. So this 1 represents the 1 in fp, the equivalence class of 1 in z mod pz, right? So you look at this polynomial. There's a multiplicative identity of the field z mod pz. So this is x to the power, x to the power p minus x to the power p minus 1 minus 1. Then Fermat's little theorem says this satisfies where all integers cannot divisible by p. In particular, the elements 1 bar, 2 bar, and p minus 1 bar in p satisfies this, right? So this is p minus 1 root. It's a coefficient polynomial over a field with leading coefficient 1. So it has already p minus 1 roots, you know. So the polynomial breaks into linear factors, x to the power p minus 1 minus 1, where this 1 is the 1 in fp, is x minus 1, when this 1 is in fp, 1 equals class of 1, x minus 2, x minus p minus 1, right? So in particular, if I put x equal to 0 on both sides, then what do you get? You get minus 1, minus 1, minus 1, p minus 1 time, which is even number. So you get 1 times 1 into 2 into p minus 1. These are elements in as considered as element in fp. 1 into 2 into p minus 1, and on the right hand side you get minus 1. So that so the equivalence class of 1 into, so it means that the equivalence class of 1 into 2 into p minus 1, their product is minus 1. The equivalence class of minus 1 in fp. That's what this shows. Okay, the product of this 1 bar, 2 bar into p minus 1 bar is minus 1 bar in p. Box of 1, box of 2, box of p minus 1, p minus 1 in a p. So p minus 1 factorial. In other words, if I write in the mod notation, then p minus 1 factorial is, yeah, so this is called Wilson theorem. And putting x equal to 0, we get minus 1 to the power p minus 1 into 1, 2 up to p minus 1 is minus 1. So this was the proof. So p divides p minus 1 factorial plus 1, or p minus 1 factorial is minus 1 mod. And I told you after that, if n is a composite number, then this is not true. Uh, so if n is a composite number, then n minus 1 factorial is minus 1 mod n. This is not true. So this is not equal to minus 1 mod n. And if n is a composite number and n is, this is not equal to minus 1 mod n. So the small typo here last time, writing error. So now I'm correcting it. N minus 1 factorial is not equal to minus 1 mod n. And if n is composite and n is greater than 4, then n minus 1 factorial is actually equal to 0 mod n. Okay, so n minus factorial is actually divided to 0. So then you can say that p is a prime if and only 2 minus 1. And for 4 also, 4 minus 1 is 3 factorial, and 3 factorial is 6, and it is equal to 2 mod 4, so which is not. This is, sometimes this version is also called Wilson. Okay, so p minus 1 factorial is minus 1 mod p if and only if p is a prime. This is called Wilson. Now we move on to a different topic, which is prime ideal and maximal. So again, let's take A to be a commutative ring with 1. Okay, and element x in A is said to be a unit if there exists y in A such that xy equal to yx equal to 1. Okay, so an element is said to be a unit if an element x is said to be a unit if there is another element y such that x times y equal to y times x equal to 1. So I have used this term many times, but just for formality, I'm defining it again. So an ideal I contains a unit, uh, then it contains that element x into y, so it will contain y. So ideal will become whole ring. Okay? So an ideal usually doesn't contain unit unless ideal is your whole ring. So this is just for completeness. I'm redefining it. Concept of unit, which is sort of I've used already. So next is prime ideal. An ideal I is said to be a prime ideal if AB belongs to I implies. So maybe I should say an element. Maybe I should first. Maybe I can swap this. So an element x in A is said to be a prime element, or simply a prime, if the ideal generated by x is a prime ideal in A. Okay. Okay. So an ideal is said to be a prime ideal uh, if AB belongs to I implies A belongs to I or B belongs to I, or equivalently, uh, I so an element is said to be a prime if something is a prime ideal. And what is the definition of prime ideal? So an ideal I is said to be a prime ideal if AB belongs to I implies A belongs to I or B belongs to I. So if AB product of two elements belongs to I, then at least one of them belongs to I. Either A is in I or B is in I. Or equivalently, I is called a prime ideal if A mod I, the quotient is an integral domain. Okay? So if the quotient is an integral domain, then we call I to be a prime ideal. Uh, so here, okay. So why these two are equivalent? Let us see just a moment. So okay, and let us get back to this definition. What does prime element be? An element being prime means? if so, maybe I should say this later. So if AB belongs to X, implies A belongs to X, or A. So that means that if X equal to if X due, so if AB, if if that is if X divides AB in A, then X divide A or X divide B, A. That is AB equal to lambda X or lambda in A plus A equal to X mu in A, or B equal to delta X equivalent to A X is okay. So an element X is said to be a prime element if look at the ideal generated by X. If AB is in that ideal, then either A is in that ideal or B is in that ideal. And what does that mean? That means if X divides AB in A, then X divides A, either A or X divides B. That is, if you want to say what is the meaning of division, because the abstract ring, it means if AB equal to lambda X for some lambda in A, then already A equal to some mu X for some mu in A, or B equal to delta X for some delta X. That is, the ideal X is a prime ideal. What is the meaning of ideal X is a prime ideal? Because I have not defined what is a prime ideal. So I defined it immediately later. That's why I put it in a different color. So an ideal I not equal to whole ring. Okay. So if something you want to call it a prime ideal, then by definition it's not equal to whole ring. Then that ideal is said to be prime ideal if AB belongs to that ideal, implies A belongs to that ideal, or B belongs to it. Now I am claiming this is equivalent to I is a prime ideal in A if and only if A mod I is an integral domain. So why is that? Let's see. So if what is the definition? If AB belongs to I, then A belongs to I or B belongs to I. That means what? In the quotient ring, A bar, B bar equal to 0 bar in A mod I. AB belongs to I means in the quotient ring, the coset of AB equal to 0. If that is 0 in A mod I, then if and only if A is 0, the A itself is in I, so A is 0 in A mod I, or B equal to 0 in A mod I. That precisely means A mod I is an integral domain, right? So that's why this is criteria. Conversely, if A mod I is an integral domain, then you take any A bar, B bar in A mod I. So A bar, B bar equal to 0 implies A bar is 0 or B bar is 0. So if you translate in this language, what is the A bar, B bar equal to 0 bar means in A mod I? That means AB bar equal to 0 bar in A mod I. That means AB belongs to I, right? Because A bar is the coset of A plus I, B bar is the coset of B plus I, 0 bar is the coset of 0 plus I, right? So that is the meaning. So it precisely you get back this definition. Okay, so this is the definition of prime ideal, and similarly you get back the definition of prime element. So X is a prime element if the ideal generated by X is a prime ideal. So there is corresponding concept of units, because when you learn primes in school, you would have seen that an element is said to be prime. It cannot be decomposed any further. So in this ring theoretic language, that is in fact called irreducible. Assume A to be an integral domain, then an element X not equal to 0 and not a unit is said to be an irreducible in A if X equal to AB implies either A is a unit or B is a unit. Okay. So either A is a unit in A or B is a unit. Then you call uh, so either A is a unit in A or B is a unit in A. Then you call Uh, so it cannot be broken further. Then you call it irreducible. So if you break it into A times B, so irreducible is only defined. So prime ideal is defined only for ideals which are not, which are like not equal to the whole ring. Similarly, irreducible is only defined for non-zero and non-unit element. If an element is unit, then it is not, by definition, not irreducible. Okay. So you take a non-zero non-unit element. What was unit? I just recall it is the set of elements which is an inverse. So an element x which is not equal to zero, not equal to unit is called irreducible. It cannot be broken further. In the precise sense, if you write it as a b, where so the either a or b is a unit. Okay. So so basically, like in Z, you know, 2 cannot be written as 2 you cannot write as some m times n unless your m and n are like the only way you can write is minus 2 into minus 1 and so on, where minus 1 is a unit, or into minus 1 into minus 1 into plus 1. Only this way you can write. So 2 cannot be broken further unless one of the element you write is unit. Okay. So next is maximal ideal, concept of maximal ideal. So this is the concept of irreducible. We'll see what is the relation between them. We'll see lots of examples. So let me go through the definition first. So maximal ideal, an ideal is said to be a maximal ideal if it is not contained, it is if it is maximal with respect to the set theoretic inclusion, meaning it is not contained in any bigger ideal. So by definition again, ideal is maximal ideal only if it is not the whole ring. So whole ring by definition is not a maximal. So maximal, an ideal is said to be maximal ideal if J is any ideal which contains I. If it contains I strictly, then J has to be equal to it. Okay, there is no bigger ideal which contains I. Okay, then it's called maximal ideal. So actually, all maximal ideals are prime. So here we are saying an ideal A is maximal if and only if A mod I is in field. So let us see why that is the case. So an ideal is, so we'll come back to this later. First, let us understand this ideal I in A is maximal if and only if the quotient by that ideal is a field. So if I is a maximal ideal, then you look at A mod I. So this direction, suppose it's a maximal ideal, then you look at A mod I. And it is easy to see. So exercise, first we do this exercise. There is one-to-one correspondence between ideals A mod I and the ideals between the ideals of there is a one-to-one correspondence between the ideals of A mod I and the ideals of A containing I. Okay. So in fact, so if you have an ideal J uh, and ideals of mod I are given by so excuse me. So the ideals of A mod I are given by part of the form J mod I, where J is an ideal of A mod I of A set containing I. Okay. So every ideal of A mod I is given. uh, is of the form J mod I. So if you have an uh, ideal J of J containing I in A, then you send it to J mod I. So this is X plus I, where X belongs to J. This is an ideal in this is inside A mod I. Conversely, if you have an ideal in A mod I, then it will be of the form. You look at his inverse image. You look at his inverse image in A, and that inverse image. So this will give you one-to-one correspondence. That inverse image will be an ideal, and then the ideal here will be of the form J mod I, where J is that ideal back in I. Okay. So once you do this, then this exercise is easy to see. So if you have an ideal of A mod I, so let's assume I now. Let us come back after this exercise. Okay, so you do this exercise, and sorry. So once you do this exercise, then you take an ideal A. So then you take an ideal I maximal in A. Then you A mod I, if if so if J mod I is an ideal A mod I such that J mod I is not equal to A mod I, and it is not equal to 0. Okay, so 0, let's say 0 strictly contained in J mod I, strictly contained in J mod I. Then J will strictly contain I. So we have to check this, and that is a contradiction, as I is maximum. Okay? So you can find an element in J which is not in I, right? Because J mod I is not equal to 0. Okay, and uh, because it's not equal to uh, uh, A mod I, so one will not belong to J, and this will be a contradiction as I is maximum. So that means J mod I, only ideal of A mod I are 0 and A mod I. So if you take any non-zero element of A mod I, that will give you generate whole of A mod I. So any non-zero element of any non-zero element x bar of A mod I generates the ideal x bar equal to x bar is unit in A mod I, right? So so okay, so 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 this implies that so x bar is a unit in A mod I, so that means every non-zero element A mod I has a multiplicative inverse mod I implied A mod I is a field. Okay, so how did we prove it? So if we assume that I is a maximal ideal, then A mod I, the only two ideals are zero and the whole ring A mod I. Because if there is a ideal intermediate between 0 and A mod I, then that ideal corresponds to an ideal in A which strictly contains I, but is not equal to whole of the ring A. So that is a contradiction to the fact that I is a maximal ideal. So no such ideal exists. So there are only two ideals in A mod I. So which means if you take any element, non-zero element of A mod I, then that non-zero element generates the whole ring A mod I. So if you take any non-zero element, then generates the whole ring A mod I. So that means in particular it contains one. So there is another element, the principal ideal X generates the whole ring A mod I. So that means one in particular belongs to the ideal generated by X bar. That means there exists Y bar so that X bar times Y bar equal to 1. So that means X bar is unique. But X bar was arbitrary. So any non-zero element has a multiplicative inverse. So any non-zero element is unique. So it is a field. And you can reverse the step. If A mod I is a field, then every non-zero element has a multiplicative inverse. That means, so you can reverse the step. Reverse the steps. Okay. So we can reverse the steps. So if A mod I is a field, every non-zero element has a multiplicative inverse. So every non-zero element is a unit. So ideal generated by any non-zero element equal to the whole ring. So the ring has only generates the whole thing. So if there is an ideal which contains I in the ring, if there is an ideal which strictly contains I and not equal to the whole ring, then that will give you an ideal in A mod I which is not equal to the whole ring and not equal to zero. But that is a contradiction because yeah, so that would be a contradiction because that will be a contradiction because then that element will not be a unit. So that means there is no ideal between I and the whole ring. So I is the maximum. So in particular, since it's a in particular, A mod I is a integral domain. It's an integral domain because if he implies I is a prime ideal. So every maximal ideal is prime ideal is a prime. Now here is one thing I want to say about this existence of the maximal ideal. There is some technicality here for a general ring. So you will think that if I give an ideal, then there is a maximal ideal containing that ideal, and that fact is actually quite non-trivial for a general ring. Although for some PID and all may not. There is a class of ring for which it is true, but not for arbitrary ring. You cannot prove or disprove this. So there is something called axiom of choice or a Zorn's lemma set theory. So it basically says one of the equivalent formulation is that that product of non-empty uncountable product of non-empty set is non-empty or arbitrary product of non-empty set is non-empty. So if you assume this axiom, so so these are like technical tests from set theory. So if you assume axiom of choice, then if you assume axiom of choice or Zorn's lemma, then if I is an ideal, then there is exist and you can show that there is a maximal ideal containing I. So we'll assume this fact. We'll assume that every ideal is contained inside. If I give you an ideal and if I give you a commutative ring, then there is a maximal ideal containing that ideal. Okay. Okay. Yeah. So one more definition, a related definition. An element X is said to be a divisor of zero. an element x, a non-zero element is said to be a, maybe I should put it here. So one final definition. So saw the definition of we saw the definition of prime element, prime ideal. We saw the definition of unit, prime element, irreducible element, prime ideal, maximal ideal. Final definition in this uh, bunch is the definition of a zero divisor. So any element x not equal to zero is said to be a divisor of zero, or a zero divisor. So a non-zero element x is not equal to zero is said to be a divisor of zero or a zero divisor in a, if there is an element y not equal to zero, so that x y equal to zero. If there an element is said to be a divisor of zero, if there's another non-zero element and you multiply by that element, then you get zero. So such thing cannot happen if you recall the definition of integral domain. Here it cannot happen. If you have a non-zero element, then if you multiply by another non-zero element, then you always get zero. Okay, so such thing cannot happen in a integral domain. But uh, uh, on the other hand, you take the ring Z mod 6Z, then you know 2 bar into 3 bar is 0 because 2 bar into 3 bar is 6. So 2 is a zero divisor in Z mod 6Z, and same is, and so is 3. 3 is also a divisor of Z. So there are examples. In integral domain, there is no divisor of Z. Okay, so now we talked about, let's see a lot of examples. Uh, we saw examples of, excuse me, we saw examples of uh, uh, so mm, all these definitions we gave, let us see examples. Okay, so examples of prime, irreducible, prime ideal, and maximal ideal. Okay, maximal. Okay. So, for example, let's start with the obvious example. The ideal zero is always the ideal zero is a prime ideal if and only if A is an integral domain. Right? What is the definition? That xy belongs to zero. Belongs to zero means if xy is zero, then either x equal to zero. Right? This was the definition if you recall. Xy equal to zero implies x equal to zero or y equal to zero. Right? This is what the meaning of an ideal. So the ideal zero can be a prime ideal, and if it is a prime ideal, you can only uh, the ring is an integral domain. As I already said, every maximal ideal is a prime ideal. And the ideal zero is the maximal ideal if and only if A is a field. So what is the when is zero is maximal ideal? There is no ideal between zero and the whole ring. So any non-zero element you take and you consider the principal ideal general by that element, that becomes the whole ring, right? So x not equal to zero implies ideal general by x equal to the whole ring A. So that means if you contain A contains one, so one belongs to the ideal general by x principal ideal. That means there exists y in A such that x times y equal to 1. Right? So x is an inverse, every non-zero element is an inverse. For all x not equal to 0 in A, this happens. So that means ideal 0 is a maximal ideal. Then every element has an inverse. So the ring becomes field. Or you can simply say you take A mod 0, then it is isomorphic to A. So if 0 is a maximal ideal, then A mod 0 is a field. But A mod 0 we know is isomorphic to A, or you can check that A mod 0 is isomorphic to A. So if A mod 0 is isomorphic to A, then 0 is a so A mod 0 is a field and A mod 0 is isomorphic to A, so A is a field. So you can check why this is true easily. Let us see some more examples. The prime number P are irreducible and prime elements in Z, and the ideal PZ generated by P are prime ideals and also maximal ideals. This is simply because Z mod PZ is a field, so it's an integral domain. That means PZ is a maximal ideal. Because it's a maximal, it's a prime ideal. And but Z is an integral domain but not a field, so 0 is a prime ideal but not a maximal. Okay, so 0 is a prime ideal but not a maximal ideal Z. And so these Also, how do you check that this is an irreducible element? So you can check any prime element cannot be written as a product of two irreducible element, but I will anyway prove it in more generally in a minute. But in any integral domain, every prime element is an irreducible element. Okay. So this is the definition you have seen in your school. As I said, that an element is said to be prime if it cannot be broken further into product of integers. But here in the ring theoretic language, we call it irreducible. Okay? And in case of Z, irreducible are equal to prime, but that need not be always the case. Okay, so if F is a field, then the polynomial ring Fx, X is a maximal ideal. Okay, and that is because you have Fx and you take quotient by X, then you can check that this is isomorphic to F. Okay, right? Because you are taking all polynomials and you are going quotient modulo the principal adjacent by X. So what you are going quotient by? So every polynomial, only polynomial is constant term remains in some sense, right? If you have fx, then a0 plus a1x plus a2x squared. So if you have a0 plus a1x plus an x to the power n, so all this is in the ideal gen by x, this part, right? So only this is same as a0 plus x, right? So this plus x is same as a0 plus x. So the only classes which remain are given by constant polynomials. This is isomorphic to f. We can check. So x is a maximal ideal. Similarly, in the two variable ring cxy, cx mod x minus a, y minus b, this, sorry, cxy, excuse me, you can check again that this is isomorphic to C for any a, b, and c. So this is again x minus a and y minus b are maximal ideal in Cx. Okay, in fact, x is a maximal ideal, and I can say that any x plus, if f is a field, then any ax plus b, you can similarly check ax plus b, where a not equal to 0 is the maximal ideal. Okay, and you can in fact check that fx mod ax plus b, that's multiplied if a is not equal to c. A, B are in fact. Okay, so you can check this. Okay. So all linear polynomials gives you maximal. So in fx, the ideal gen by x square is not a prime ideal. Okay. That is because you take fx mod x square. So this is here you take x bar into x bar. This is equal to x bar squared, which is equal to 0, but x bar is not equal to 0. Okay, because then if x bar equal to 0, that will mean x belongs to the ideal gen by x square. That it means that x can be written as x squared times some fx, and then here degree is greater or equal to 2, right? And then here the degree will be x squared times fx. So here the degree will be 2 plus degree of fx, but here the degree will be 1. So, so degree, here degree. Here degree equal to 1, and here degree is greater or equal to 2. Okay, so that will give you a contradiction. So x bar is not equal to 0, but x bar into x bar equal to 0. That means this is not an maximal ideal. It's not a prime ideal. Okay. So the lemma, next lemma we want to prove, in an integral domain A, every prime element is an irreducible element. Okay. So let P be a prime element in an integral domain A, and if P equal to AB, where AB are in A, then AB belongs to P, a prime ideal. So either A belongs to P, A equal to lambda times P. So I want to prove that whenever you have an integral domain. So by the way, irreducible, one thing to notice here, the irreducible element I have only defined for prime ideal, I have defined for any ring. So irreducible element, I just want to emphasize, irreducible element is only defined for integral domain. Okay? I have not defined irreducible element otherwise. Okay? Whereas the prime ideal and maximal ideal is defined for any ring. Okay, so A is any ring here. Here, standing hypothesis A is a commutative ring with identity. So for any commutative ring with identity, I have defined unit, I have defined prime element, I have defined prime ideal, I have defined maximal ideal, but the irreducible element is only defined for integral. So keep that in mind. So, and in an integral domain, every prime element is an irreducible element. So why is that? So let P be an prime element in an integral domain A. Suppose P equal to AB, where A, B are element of A, then so if possible, so I have to show P is an irreducible element. So let's say P equal to AB, where AB are in A. Then AB belongs to the ideal generated by P by definition, because AB equal to P and P is an element of the ideal, so AB belongs to P. And P is a prime ideal. So either A belongs to the ideal or B belongs to the ideal. So what does it mean? A belongs to the ideal, A equal to some lambda times P, lambda is in A. Or you can say or B equal to some mu times P, where mu is in A. So let's say the first one happens, proof is similar. Okay? So that's why I said say either A is some multiple of A multiple of P or B is some multiple of P. So if P equal to lambda times, so if A equal to lambda times P, if it was B, we'd have argued the same way. Then A becomes, so what do you get? A becomes lambda P times B because A is lambda P. So P into 1 minus lambda B equal to 0 and P is not equal to 0. Uh, so let's say P B, so P, so we assume, so when you talk about element, let's say P is not equal to 0 because irreducible is, so every, so let's say non-zero, let's just say. So when you talk about element, prime element, let's just take every non-zero because the ideal 0 is also prime ideal in Z. So to avoid in an integral domain, so let's say non-zero prime element is an irreducible element. So irreducible element are defined for integral domain, and non-zero element can be irreducible element. So let's say P is a non-zero prime ideal element, then I have to say it's an irreducible element. So P is not equal to 0 here. So that means because it's an integral domain, then 1 minus lambda times B has to be equal to 0. So lambda B equal to 1, so B is a unit. So thus P equal to AB implies if A belongs to that ideal, then B is a unit. If it was B equal to mu times P, then we would have got we would have put A is a unit. So at least one of them, A or B, is a unit in A. So P is irreducible. So we prove every non-zero prime element is irreducible in any integral domain. Next time we'll see, but every irreducible need not be prime. Irreducible element in an integral domain need not be prime. However, in a PID, every irreducible is prime. So we'll start with this next time, and then we'll see some example of as example. This will be important to us in our subsequent thing that irreducible element need not be prime. So concept of prime is stronger, and in some sense that's why this is the correct definition when we take this definition. So we have seen every non-zero prime element is irreducible in any integral domain. However, we'll see examples of integral domain, which is important in our number theory context, where irreducible element need not be prime. Okay. So we'll continue again next.